हॅलो हॅलो बस का रे.
हा आवाज त्याच्यातून तिकडे जाणार आणि ते इथं प्रेझेंट आहे कशाला मीट जॉईन करून राहिले इको इन झालं त्याच्यामध्ये इथं प्रेझेंट आहे तर मीट तर जॉईन करू ना तुम्ही बाकीचे सगळं मीट बंद झालं म्हणजे एकदम करा माईक बंद करा तुमचा माईक बंद करून इकून यायला पाहिजे समजा इको आला बॅक कॅमेरा दिसून राहिले त्याच्यानंतर वाटलं जॉईन Professor Devraman says success can come to you by courageous devotion. The task lying in front of you.
Very warm good afternoon. Happy welcome to all visit Children College. Oh. Department of Physics. We are welcoming all representatives for the celebration of National Science Day. As we all know that today we are gathered here to celebrate National Science Day. The whole world is started with a strong role of science. Dr. C.V. Raman put the nation on the world map in the field of science. Sir C.V. Raman was one of those global men. He discovered the Raman effect, which studies the scattering of light in solid, liquid, and gases. For his invention, he received the Nobel Prize for Physics in 1930. Therefore, the government of India dedicated 20th February as National Science Day from 1999. So, Ashwini, can you tell us what is Raman effect? Yes, Chetan, of course. To know that what is Raman effect, we will have to see a short video clip. So, please share the video clip.
In 1928, Sir C.V. Raman discovered experimentally that the ultraviolet light is scattered when it is allowed to pass through a substance. The scattered frequencies other than that of incident frequency. This is known as Raman effect. Raman lights. The lights whose frequencies have been modified in Raman effect are called Raman lights. The lights having frequencies lower than the incident frequency are called Stokes lights, and the lights having frequencies higher than the incident frequency are called anti-Stokes lights. What is Raman spectrum? The Raman effect can be easily understood by considering the scattering of photons of the incident light within atoms or molecules. Applications of Raman spectrum. It is widely used in almost all branches of science. Raman spectra of different substances enable to classify them according to their molecular structure. In industry, Raman spectroscopy is being applied to study the properties of materials. It is used to analyze the chemical constitution. Thank you for watching. Please subscribe to the channel.
For this immense contribution to the world by Dr. C.V. Raman, sir, please give a big round of applause for him.
Yes, sir.
Now I would like to request Professor Gedam sir to welcome the President of the Dr. Nanoty, Principal of the Identity College of Science, Agrawal.
Now I would like to request Professor Agrawal sir to welcome Professor Gedam sir for offering class.
I would like to request Jaiswal sir to welcome Dr. Agrawal sir. I would like to call the Muley to welcome Jaiswal.
I would like to call Priyanka Khandari to welcome Ms. Muley ma'am.
I would like to call Miley to welcome I would like to request Agrawal sir to welcome Rahatgaonkar. Now I would like to request Professor Gedam sir, who is the convener of today's program, to give an introductory speech about today's program.
And also I welcome Dr. Muley sir and Amravati. We are gathered here on the auspicious occasion of National Science Day in the memory of the history of great Roman Dept on 28th April 1928. I want to give short introduction of this team. Sir C. Raman actually was a brilliant student from his childhood. He born on 7 November 1888 at Jerusalem. He taught the bachelor degree of exam in the University of Madras with honor physics from the Presidency College at the age of only 60. He published his first research paper on the reflection of light. Then he is a graduate student. He is very much interested in research, but because of his father's influence, he passed the exam of Indian Finance Service and joined as an assistant accountant general in Calcutta. But at the same time, he is very happy to see first research institute in Calcutta, that is Indian Association of Cultivation of Science, where he later discovered the Raman effect. It is nothing but when a beam of light passing through transparent medium are scattered to different frequencies, and then the incident frequency, that is with higher and lower frequency than the original frequency, which calls for an anti-slope band. For this discovery, he gave a Nobel Prize in 1930. It was a great news for all Indians and Asians because he was the first Asian to get Nobel Prize in science. Sir C.V. Raman achieved many awards in his life, but the government of India honored him with the highest civilian award in India, that is the Bharat Ratna in 1954, or in Great History of Raman. Therefore, to encourage the students, people towards the science and technology, Government of India decided to celebrate National Science Day at every year and on 28th. It's tribute to the Raman effect. So, in this year of 2022, the theme of National Science Day is integrated approach in science and technology for sustainable future. Therefore, we hope in future from the inspiration of the Raman effect as a Nobel Prize winning experiment, all the scientists, researchers, students, teachers among the India are come together and create interdisciplinary approach and produce a concrete work which is helpful for the mankind and the nature. So, to convey this message, we are here in to celebrate National Science Day by considering the theme of integrated approach in science and technology for a sustainable future by online-based lecture on laser and its application, which is going to be delivered by Dr. Muley, Professor and Head Department of Physics, Sant Gadge University, Amravati. Therefore, with this, I conclude the introduction of this. And now I request your Chairperson and Shri to
Thank you, sir. Now, I would like to request Dr. Muley, Principal of the Nanoty College of Science, to express his thoughts and guidance for this auspicious topic.
राष्ट्रीय विज्ञान दिवस नॅशनल सायन्स डे 20 ऑक्टोबर 28 फेब्रुवारी 2022. आजच्या राष्ट्रीय विज्ञान दिवसाच्या निमित्ताने विज्ञानाच्या सर्व प्राध्यापक, कर्मचारी आणि विद्यार्थी सर्वांना शुभेच्छा व्यक्त करून डिपार्टमेंट ऑफ फिजिक्स in collaboration with the IQAC of the college organizes this function. या फंक्शनला जे उपस्थित आहे तिथे त्यामध्ये प्राध्यापक गेडाम सर, डॉक्टर रोहित अग्रवाल, प्राध्यापक जयस्वाल सर, डॉक्टर पुनमंतराव मॅडम, डॉक्टर राहतगावकर सर, आपल्या डिपार्टमेंटचे जे टीचर्स आहेत दिवाणे मॅडम आणि वीरा मॅडम, अजून बाकी जे शिक्षक आहेत ते प्राध्यापक आणि सर्व विद्यार्थी, मला असं वाटतं सगळं UG आणि PGचे विद्यार्थी दुनियाच्या पुस्तक पोस्ट ग्रॅज्युएशनच्या आपले डिपार्टमेंट ऑफ फिजिक्स इनिशिएटिव्ह पुढाकार घेऊन हा कार्यक्रम आयोजित केला. आणि आता या ठिकाणी आपण अभिवादन करतो. सर्वप्रथम मी श्री रामन यांच्या प्रतिमेला पुनश्च एकदा विनम्र अभिवादन करतो. ही आपली जुनी परंपरा आहे की आपलं सायन्स कॉलेज आहे आणि आपण 28 फेब्रुवारी दिवसाला सायन्स डेचा कार्यक्रम होतो. दरवेळेस विचारलं जातं. आज सकाळी मी 7:30 वाजता विज्ञानावरती बोल 1 मिनिट बोलत राहा म्हणतात. परफेक्ट म्हणतात सायन्स तुला काय वाटतं, सायन्सच्या माध्यमातून आपण केलेली आहे. विज्ञानातून विकासाकडेचा महामंत्र आपण घेतलेला आहे आणि आपण पुढे पुढे वाटचाल करत आहोत. सुंदर व्यक्त केल्या भावनाने मनोगत व्यक्त केला. टेक्नॉलॉजीच्या युगामध्ये विज्ञानाचं काय महत्व आहे आणि आज या महाविद्यालयाला 50 वर्ष होतात. 50 वर्ष झालेले आहेत. आम्ही सुवर्ण महोत्सवी वर्ष साजरा केला 2 वर्षापूर्वी आणि 50 वर्ष हजारो विद्यार्थी या महाविद्यालयापासून घडले आहेत. आता डिपार्टमेंट ऑफ फिजिक्स याच्यामध्ये आता आपण MSc सुरू केला. आणि मी जयस्वाल सरांना जयराम सरांना सांगितलं की आजच्या दिवशी आपण काय केलं पाहिजे. आता 28 फेब्रुवारीचं काय महत्व आहे. श्री रामन यांचं याच्यात कन्फ्युजन आहे, बरोबर आहे. मी एक वास्तविक गोष्ट त्याच्यावरती कोणी म्हणे जन्मदिवस आहे, कोणी म्हणे अजून काही आहे, तसं नाही आहे. तो रामन इफेक्ट आहे, ज्याला कुठेतरी पब्लिक झाल्यानंतर त्या रिसर्चला रेकग्नाइज केला गेला आणि नोबेल प्राइज मिळाला. त्या दिवशी 28 फेब्रुवारीचा दिवस आहे, म्हणून तो विज्ञानाचा दिवस असा गौरवने केलेला आजच्या दिवसाला. आणि आपण सायन्स डे करतो. आपण सायन्स डे करत असताना आज अनेक कार्यक्रम घेतो. ॲस्ट्रॉनॉमी डिपार्टमेंटकडनं यांनी आता दुपारी टेलिस्कोप आपण ठेवा डिपार्टमेंट ऑफ फिजिक्सच्या समोर आपल्याला लॅबोरेटरी टू मार्सेस म्हणजे केवळ आपलं रिसर्च आहे प्रयोगशाळेपुरता मर्यादित ठेवायचं आणि आपल्या लोकांपर्यंत पोहोचत, माल वैज्ञानिकांपर्यंत पोहोचत, विद्यार्थ्यांपर्यंत पोहोचत, समाजापर्यंत पोहोचत. त्यामुळे आम्ही ते टेलिस्कोप दाखवतो गावामध्ये. संध्याकाळच्या वेळेस जबाबदाऱ्यांचा अभ्यास करतो. आजही मी यांना सांगितलं की असे सर्व इन्स्ट्रुमेंट सायन्समध्ये जे आपण ज्याला ऑपरेट करतो त्या इन्स्ट्रुमेंटला आज आपण जसं एखाद्या विद्यार्थ्यांना एनर्जी मिळाली पाहिजे, ॲस्ट्रॉनॉमीच्या माध्यमातून टेलिस्कोपचं जे आहे हाऊ इट वर्क ते प्रत्येक विद्यार्थ्याला सांगता आलं. आमचा विद्यार्थी काय करतो पुढे करिअरमध्ये एखाद्या लॅबोरेटरीमध्ये क्वालिटी कंट्रोल विभागात लागतो, पुढे सायंटिस्ट होतो, जिथे पुढे जातो. एखादा इलेक्ट्रॉनिक्सचा विद्यार्थी शोल्डरिंग मशीन हातात घेऊन पुढे काही लॅबमध्ये काम करतो, मायक्रोस्कोप घेऊन त्या विषाणू जीवाणूचा अभ्यास करतो. विषाणू तर शक्य नाही पण जेव्हा बॅक्टेरिया ऑब्झर्व करतो त्याला हाऊ टू ऑपरेट मायक्रोस्कोप येत नाही. आणि आपण विज्ञानामध्ये हे निश्चित क्रेडिट गोज टू दोज पर्सन्स हू कन्व्हिन्स द वर्ल्ड. सरांनी काही सांगितलं रिसर्च पेपर. रिसर्च पेपर आपण सगळ्यांनी विचार केला पाहिजे की मी एक संशोधन करेन आणि मी एक पेपर काय निबंध लिहिला की शाळेमध्ये निबंध येत होता आपण लिहिला, त्याला शोध निबंध म्हणायचं. आता शोध निबंध आपण पब्लिश करा. मी आपल्या अकोल्यातून मोरणा नदी वाहत त्याच्या पाण्याचे सॅम्पल 5 ठिकाणून आणले आणि पुढे जास्त प्रदूषित आहे म्हणून असं एक लहानसा प्रयत्न केला की मोरा पुलाच्या खाली तिकडे बायपासवरती मोरणा नदी दगडी पुलाच्या खाली अकोल्यामध्ये अलग अलग स्टॉपवर पाण्याचे सॅम्पल आणले आणि बॅक्टेरियल लोड काउंट केला की इथे बॅक्टेरिया किती, इथे बॅक्टेरिया किती, इथे बॅक्टेरिया. हे आपण नेटेड आहे विजिबल आपण बघतो पाण्यामध्ये पुढे प्रदूषणाचे मायक्रोस्कोपच्या खाली बॅक्टेरिया किती लोड आहे आणि त्याच्यावर एक स्टॅटिस्टिक्स तयार करून एक पेपर लिहिला. मला आनंद वाटतो की तो पेपर मी वाचला एका कॉन्फरन्समध्ये नेपाळला आणि मला ते 10-12 मिनिटं मिळाले. त्याच्यातून जे काही मला लोकांनी प्रश्न विचारले आणि मी काही मांडू शकलो ते इंडिव्हिज्युअल एक एनर्जी आपण विज्ञानाच्या विद्यार्थ्यांना त्याच्यातून पुढे वाटचाल करण्याची एनर्जी मिळते. तर पीएचडी करतात, पीएचडी झाले तर संशोधनाला भरपूर स्कोप असतो. आमच्या लॅबोरेटरी रेकग्नाइज करायची. आज आपण तो विचार केला पाहिजे. श्री रामन यांना अभिवादन करत असताना की मी एक चांगला विज्ञानाकडे भारताची प्रगती सरांनी मध्यंतरी आठवत असेल 24 डिसेंबरला एक ठाकरे नावाची विद्यार्थी आली होती सर, फिजिक्स विषय घेतलेली आणि ती पुढे काम करत होता इस्रोमध्ये काम. इस्रोमध्ये आता एकदम सायंटिस्टचे लेवल असतात. आपण सायंटिस्टच म्हणायचं. एमएससी झाली की फिजिक्स करू, बीएससी आरआयटी मोदी सारख्या लहान गावातून आले शिकायला. व्हेरी प्राऊड ऑफ द स्टुडंट्स. आम्हाला खूप अभिमान वाटतो अशा विद्यार्थ्यांना. आता मॅडम मी सांगितलं मला गणितामध्ये एक कोणी 40 नावाचा विद्यार्थी होता, स्टेट पास झाला. मला वाटतं आपल्या कॉलेजचा विद्यार्थी एक स्टेट परीक्षा पास झाला. त्या ज्या आपण वाटचाल करतो याच्यात मी आज या ठिकाणी डिपार्टमेंट ऑफ फिजिक्स स्टाफ मेंबर्सचा मनपूर्वक अभिनंदन करतो. एक चांगल्या कार्यक्रमाचा नीट त्यांच्या कार्यक्रमाचं आयोजन आणि मला माहित नाही मुलाचं जॉईन करायचं की नाही, परंतु अमरावती संत गाडगेबाबा अमरावती विद्यापीठाचे आपण संलग्नित महाविद्यालय आहे आणि विद्यापीठामध्ये जे भौतिकशास्त्र विभाग आहे, फिजिक्स डिपार्टमेंट आहे, ते विभाग करून डॉक्टर मुळे साहेब आपला इथून करून आपण जॉईन झालेले आहे. IIT कॉलेजच्या वतीने डिपार्टमेंट ऑफ फिजिक्सच्या वतीने आम्ही त्यांचं मनापूर्वक स्वागत आहे. आज आपण आमचे विद्यार्थी एकदा पुन्हा टाळ्या वाजून आपला तर आपण जॉईन झाले आमच्या स्क्रीनवरती त्या ठिकाणी तुम्ही दिसत आहात. जरी व्हर्च्युअली हा कार्यक्रम असला तरी आपली उपस्थिती आम्हाला निश्चितपणे मार्गदर्शक ठरणार आहे. महाविद्यालयाच्या वतीने आपलं स्वागत करतो सर पुन्हा. आणि एवढं बोलून माझं स्वागत करतो या ठिकाणी आरंभ करतो. धन्यवाद.
Now I would like to request Agrawal sir to give some brief information about our guest.
Very good afternoon, everyone. On the occasion of National Science Day, here we are having a very good renowned personality from the science field. Let me introduce our today's guest for and speaker, Dr. Muley. He was the professor and head Department of Physics, Sant University, Amravati. He is the coordinator of postgraduate teaching department of Dr. Babasaheb Ambedkar Course. He is also a coordinator of Buddhist Study Center and also a co-coordinator of Dr. Ambedkar Study Center, Sant University, Amravati. Moving to the educational qualification, Sir has completed his BSc from Amravati University and MSc from Amravati University with gold medal and in first class. Then he has completed his PhD from Sant Amravati University, Amravati, and his research work is on growth and characterization of laser material and non-linear systems. Other qualification, Sir has lecturer with 20% topper in 2002. Then he also qualified NET in 2001. December 2001, has also qualified as state February 2002. Sir was qualified as a DRDO state scientist D in 2002. So he is also a guest here in 2002. Moving to the teaching experience, Sir had initially joined as an assistant professor in 2001 at the College of Arts and Commerce, Mumbai, and now he has joined from 2003 to Sant Amravati University as a professor and head of the department. Sir has working in various committees. He is a member of Senate. From September 2017. As a member of Board of Studies in the Humanities and Applied Science, Humanities and Applied Science, as the Chairman of Engineering Board of Sant Amravati University, Amravati. He is a member of Board of Studies of Physics of Sant Amravati University, Amravati. He is also member of Academic Council of Sant Amravati University, Amravati. Moving to the awards and honors, Sir has achieved National Overseas Scholarship 2005 for PhD abroad, offered by the Ministry of Social Justice and Empowerment, Government of India. Sir has got a Best Service Award, University Teacher contest by Sant University, Amravati. Sir has a top cited article 2018-19. Paper has been recognized as a top cited paper in system research and technology. Sir has visited to the abroad that is South Korea to present his paper in international conference and visit the laboratory. Moving to the research work, Sir has a research area in non-linear optical properties of materials, nanoparticles, superparticles, and optical biosensors. Sir has completed This 7 research project has cost is 1,49,000. Under his able guidance, 7 students have awarded PhD and 3 students are still working. So they have published various papers in national and international papers. Nearly 140 papers have been published in various scientific journals. They have also been delivered or invited talks in various conferences and seminars. This is a brief biodata for today's guest. Thank you.
Thank you, sir. Now, it's my extreme pleasure to invite our guest to express his thoughts and guidance.
So, very good afternoon to all. Chairman of this inaugural function, Principal Dr. Nanoty sir, IQAC Coordinator, RL Rahatgaonkar sir, Convener P. Gedam sir, Dr. Agrawal sir, Co-convener, and Coordinator Dr. Jaiswal sir, other faculty members, and my dear students. Very good afternoon to all. Today we are celebrating National Science Day to remember the great invention by Dr. C.V. Raman. We proudly say it is the Raman effect. Okay, so you all of you know what is the Raman effect. So I will not upon that Raman effect. The topic, today's topic of my talk, this lecture is its application. Am I audible to all? Am I audible?
Yes, sir. Yes, sir. Please continue.
And my screen this.
Yes, sir. Yes, sir.
Okay. So the topic of today's talk is this laser and its application. And this topic, how it is, whatever the talk I am giving today, it is designed for this BSc and MSc students. So it is just an introductory lecture, we can say, I am giving. And it is about this laser and then its application. I will cover in the basics of the laser and then the basic applications of the laser. Okay, so we know the laser, we always say laser. Laser is the acronym of light amplification by stimulated emission of radiation. So we consider the initial letters of this light amplification by stimulated emission of radiation, laser. So laser is a narrow beam of light of a single wavelength. We say it is monochromatic, in which each wave is in phase. In phase means it is coherent with other near it. Okay. So laser is a narrow beam. It is, we can say it is narrow means it's a parallel beam of a single wavelength monochromatic. So you know in your darkroom laboratories in physics we use the sodium light. We say it is a monochromatic. Actually it has two wavelengths, but still we say it is a monochromatic. Monochromatic means it has only single wavelength. Okay, so your laser, it is a parallel beam of a single wavelength, and each wave is in phase, means we will say it is a coherent. So your laser is monochromatic and coherent beam of light. So the thinking about this laser radiation, it was started well in the 1917, before the invention of this laser. So explaining the black body radiation. So you know the black body radiations. The radiations are emitted by a black body. So your black body emits the radiations of all frequencies, and the peak peak at which the maximum intensity your black body is emitting. So it is depending on the temperature of that black body. So while explaining the black body radiations, so the various scientists have proposed their different models, and Einstein, they have introduced Einstein has introduced three coefficients. So he has given his theory to explain the black body radiation, and he has introduced three coefficients. We say it is AB coefficients: A21, B12, and B21. So we say it is Einstein's AB coefficients. So in this one he has introduced the one concept of stimulated emission. He introduced the concept of stimulated emission, and one of the these three Einstein coefficients B21 is corresponding to that stimulated emission. So you know the atom. The atom is composed of at the center it is the nucleus, and the electron cloud is revolving around that nucleus. Okay, so in actual your atom is a neutral one, and if you allow the incident on that atom, so it is absorbed. The photon can be absorbed by that atom. So if your atom is absorbing a photon of a particular energy, so the electron it will be excited to the another higher energy level. So we can say after absorbing the photon by the atom, it is going to, or it is raising to the excited state. Okay, it is excited state. So it can emit the radiations. It can emit the radiation. So firstly the absorption, and then there is an emission. So the emission will be of two types. One is spontaneous emission, that is it is instantly it is giving the radiations. So your atom is coming to the original state, that is we say it is a ground state, from the excited state by emitting the photon instantly or spontaneously. So we say it is a spontaneous emission. Another kind of emission which is postulated, or it is proposed by the Einstein, it was the stimulated emission. Means if your atom is in excited state, means your electron present in a higher energy level, and if another photon is coming and it is interacting with that electron, so that another electron is forcing that electron to go to the ground state, so that we say is that photon is stimulating electron to emit another photon, so it is said to be stimulated emission. Okay, so there are two kinds of emissions: spontaneous emission and stimulated emission. Spontaneous emission is the emission of photon without having the interaction with any other photon, and stimulated emission is that emission which is stimulated by the another photon. Stimulated by the another photon. So in this case, there is interaction between another photon and the excited electron. Okay. So in this process, we have this absorption, then spontaneous emission, and then stimulated emission. Okay. So spontaneous emission, in this spontaneous emission, the electron can drop back spontaneously to the ground state, emitting photons. So when your electron it is in an excited state, it will accrue the energy of, so it will emit the photons and comes to the ground state. So this emitted photon, now this spontaneously emitted photon, it don't have the coherency. So means it don't behave the property we say the coherency. That means it is not a coherent. It varies. It means it varies in phase from point to point, which it is a spatial coherence, and from moment to moment, means we say it is temporal coherent. Okay, so your photons, the spontaneously photons emitted, they are not in phase, means they are not coherent. Okay, they are not coherent. For example, you can consider any tungsten bulb, tungsten lamp, or your tube light in your house or in your any home room. So these sources are non-coherent, incoherent sources. Means the whatever the photons they are coming from these sources, the phase is not, the photons are not in phase, or the electromagnetic rays are coming out, they are not in phase. So they are not coherent. In stimulated emission, the electron it is triggered by the another photon, that is electromagnetic field of that photon. So the photon, it is interacting with that electron and forcing that electron to jump or to emit the another photon by coming or by going to the ground state. So let us consider this is photon which is coming, and they are inciding on this electron, interacting with this excited electron, and then it is another photon is emitted, and these two photons are moving in this direction. So these two photons, or these two electromagnetic waves, are in phase and of the same frequency. So here, you know, this absorption means we can say this energy level E1. Let us consider energy level E1 is a ground state, and it is occupied by this electron. And if the photon of frequency n, so it will have the energy h n. So it is inciding on this atom in which the electron is in the energy level E1. So this photon has the energy equals to E2 minus E1, where E2 is the another energy level, this is a higher energy level, which is MT1. So if this photon is inciding your atom, this electron will absorb that photon and it will move from this energy level E1 to energy level E2. Energy level E2. Okay, so this energy level E2. So we say it is absorption of the photon, absorption of the photon by the atom or by that electron. So we can say this excitation of electron from this ground state E1 to excited state E2 by absorbing photon of energy Hm. So according to Bose-Kwan statistic, if you consider there are a large number of atoms M0 at a temperature T, then the thermal equilibrium, the number of atoms in energy state E1 and E2 are given by this Bose-Kwan distribution function. N1 is equal to N0 into e raised to power minus E1 upon KT, where N1 is the number of atoms in state E1 at a temperature T, where N0 is the total number of atoms, and N2 is the number of atoms in the excited state E2. It will be equal to N0 into e raised to power minus E2 upon KT, where here you know this K is the Bose-Kwan constant, is the temperature, E1, E2 are the energy levels, energies of these two energy levels E1 and E2. Okay, so in this case, certainly you know E1 is less than E2. E1 is less than E2. This energy level E1 is less than E2, and if E1 is less than E2 and N1 is greater than N2. N1 is greater than N2. So this is a general case. We have, so excitation is not so strong, so we can have this type of situation. But if you consider E1 is less than E2 and N1 is less than N2, N1 is less than N2 means number of electrons in the energy level E1, number of electrons in the energy level E1 are less than the number of electrons in energy level E2. Number of atoms in excited states are more than the number of atoms in a ground state. So we say it is a population inversion. We say it is a population inversion. What was the initial population? The more electrons were in a ground state. So if you consider the N0 number of atoms, and out of this N0 atoms, maximum were in having the electrons occupied lower energy state E1, means the maximum were in a ground state. But if you consider the situation is such that N1 is less than N2, means more number of electrons are in excited state, means more atoms are in excited state and less number of atoms are in ground state. So here is inversion of population. Inversion of population. So in order to get the lesser additions, we require population inversion. We require population inversion. So this is a tendency, always tendency it is always that every atom or in nature everything it will tries to have the ground state, lower energy state. So everything it tries to have the lowest energy state. So certainly atom and it is in excited state, it will try to have its ground state. Pardon?
Hello, sir.
Huh?
Sir, screen is stopped. Now it is okay. Okay. Okay, sir. Continue.
Oh.
Now it is synced.
Okay, so if you consider this, we are talking about the population inversion. So every system it tries to have this ground state. In nature, everything it will try to occupy the lowest energy state. So if you say your atom, it is in a excited state, so it will try to come to the ground state. So certainly it will emit the extra energy and it will come to the ground state. So if this is the situation, then what will happen? You cannot have the population inversion. Means there will be no number of electrons, more number of atoms in a excited state than the ground state. But in order to have the lasing action, that is, in order to get the lasers from this system, we require population inversion. So it is if you consider the energy level structure, so generally the excited state have very less lifetime. It is of the order of nanosecond 10⁻³ nanosecond. So if the electron moves from the ground state to the excited state, so it will come back from the excited state to the ground state by emitting the photons. But other kinds of energy levels are there. In which electron can reside, can stay for a longer duration. So we say it is a metastable states or metastable energy state. So here it is given in this picture. You will see in the diagram E2. It is serving as a metastable state. So which has the lifetime around 10⁻³ to 1 second. Okay. So once your electron it is excited from the ground state E1 to the excited state E3, higher energy level E3. So it will emit some energy in the form of either photon or heat, and it will come to the energy level E2. So E2 is the energy level which has very longer lifetime as compared to the lifetime of electron in state E3. So you will see here that the lifetime of the electron in state E3 is 10⁻⁹, and here in E2 it is 10⁻⁻3. If you consider it is 10⁻⁻3 second. So here is your electron, it will reside for a long duration. So if your excitation is so strong, so so many electrons it will be excited from state E1 to E3, and then these electrons from E3 it will comes to the energy level E2, and you will see there is accumulation of electrons in energy state E2. So the situation will reach that the number of electrons, that is concentration of electrons in energy state E2 is greater than number of electrons in state E1, and we say it is a population inversion. And if any electron trigger this the electrons in the state E2 to emit stimulately, or to stimulate to emit the radiation. So bunch of electron it will come from energy level E2 to energy level E1, and it will emit a lot of radiations at a time, and all these pulses, it will be in a phase and upper same wavelength, so you will get the laser. You will get laser. Okay, so this thing is happening. It means you are getting the laser radiations only when there is a population inversion, and you will get the photons of the same frequency, same wavelength, and all these pulses, it will be in phase. Okay, so you will get the laser radiations. So to get to generate the laser beam, there are three important processes we require in the lasing system. One is population inversion. We have already seen what is the population inversion. Population inversion means there is a more number of electrons in excited state than the ground state. Stimulated emission means the radiations we have seen. Stimulated emission, the radiations emitted by the jumping electron from excited state to ground state in the presence of another proton. And another one is an important thing we require, is pumping source. Yes, we require some mechanism to excite the electron from ground state to excited state. So we say it is a pumping. We require pumping source. It is pumping mechanism is there. So there are different kinds of pumping is used. It is optical pumping, electrical pumping. Okay, so this your general laser system, it is of this kind. It is shown in this uppermost figure. It is in this one. This is medium. It is a lasing medium. We say it is a lasing medium. Then it is pump source. Means these are the this pump. It is pumping the electrons from ground state to excited state. And here is back mirror. It is reflector, which reflect all of the radiations in the medium. And here is another mirror at the output, which is partially mirror. So some of the portion of your radiations is reflected back, and small portion it is transmitted. You will get collimated laser beam at the output. So this is the this kind of your laser system. We have this type of components: medium, pump source, and this mirrors. This back mirror and front mirror, we say it is a laser cavity in which this laser medium is placed. Okay. So here it is another one. This lower figure, it is active medium. There is laser medium, excitation mechanism. This back mirror, we say it is a high reflectance mirror. It is reflecting almost all the radiation in your back to the active medium. And this output mirror, it is a partially transmitting mirror. We say it is output coupler, and these two mirrors are providing feedback mechanism, that is maximum of energy. It is sent back to the active medium, so that there must be a population inversion. Okay, there must be a population inversion. Okay, so this firstly the stimulated emission, it was proposed by the scientist by the Einstein in 1970. Okay, 1970. And after that, initially there was a measure, that is microwave stimulated emission by radiation measure. And this is laser. It was people were thinking there is stimulated emission of radiation in microwave region. So we say it is a measure. It was operating before the invention of the laser in 1960. So before this one, people were thinking there is a laser in a microwave region. So why should not be the optical radiations? That is, we say it is a visible radiation region from 400 nanometer to 700 nanometer. Why there should not be a stimulated emission in optical region? And people were trying to develop laser. So in the first laser, it was developed by the scientist Mayman in 1960. So he has used this Al2O3 doped with chromium Cr3+. So we say it is a ruby laser. So it is pink color, ruby color, it is rod, and it is excited with this flash lamp, flash tube. So in this figure you will see this is the ruby rod, and it is excited with the flash lamp, and it emits the monochromatic coherent light of the wavelength 694.3 nanometer. Okay, so this was the first laser. It was designed and operated by the scientist member, who said it is a ruby laser. So after ruby laser, so many lasers have been investigated, and we are using so many lasers. So there are three kinds of pumping mechanisms. So we have the optical pumping. So here we require pump mechanism, this excitation mechanism. So there are three kinds of excitation mechanism. One is the optical pumping, so which is suitable for this liquid and solid lasers because they have a wide absorption band gap. So we can use optical pumping. Electrical pumping, it is suitable for gas laser because gas has a very narrow absorption band. And then another one is a chemical reaction. Okay, so these are the pumping mechanism. We can have this lasing medium, active medium. It may be solid, it may be liquid, or it may be a gaseous. Okay, so we can have this these three types of lasers. One is solid laser, that is active medium is solid. The active medium is liquid, so we have the liquid lasers, and then gaseous laser. So the example of the solid state lasers are ruby laser, which is firstly investigated. Then neodymium doped glass laser, that is we say it is an ND glass laser. This ND laser, we say it is ND yttrium aluminum garnet laser. So it is, these are the example of solid state laser. Liquid lasers are the dyes lasers. So in which dyes are used, and the dyes are excited by the light, and then you will get the lasers. Gas lasers. So there are so many gas lasers. HENE gas laser you use in your laboratory. Argon laser, carbon dioxide laser, HECD lasers, nitrogen laser, KR laser, excimer laser. Okay, so these are the types of lasers: solid lasers, liquid lasers, and gas lasers. Okay, so this is the systematic diagram of this dye laser, schematic diagram of dye laser, in which here this energy source, that is pump beam from the argon laser, is generally used, and it is allowed to incident on this flowing dye, and dye is excited and it emits the laser radiations, and then it is high reflector is used here, and here is tuning element, and you will get the tunable output at the you will get the tunable laser at the output. Okay, so this laser dye laser emits so many radiations, and we can select any one from this one, and we get the dye laser at the output. This is Nd:YAG laser. In Nd:YAG laser, you have the Nd:YAG crystal, cylindrical crystal. It is excited by the iodide pumping lamp, tungsten iodide pumping lamp, and then these are the, as usual, it is a high reflecting mirror at the back, and the coupler, output coupler, which has the transmittance around 2.5%, and you will get the Nd:YAG laser. Okay, so Nd:YAG laser, it is in a IR region, it gives 1064 nanometer. Okay, so here after this one we have, since there are how you are getting the laser, that is mechanism of laser, that is actually absorption by the your active medium, means we have to excite the active medium with a certain mechanism. It is either by optical pumping or electrical pumping, another one is chemical pumping. Okay, then there is a spontaneous, there is a population inversion, and then stimulated emission. So finally you will get the laser beam, and laser beam, it will have these peculiar properties. very interesting property is coherent. This laser beam is coherent. Means all the photons or the electromagnetic pulses are in phase. Another property is this monochromatic. Means it has only single wavelength. It is a single wavelength radiation. Then it is collimated, means highly parallel. Divergence is almost zero. So divergence is very less. It is collimated, and then it is intense. It is concentrated. Intensity is very large. So your laser beam has these three peculiar properties. So these peculiar properties, important properties, because of these important properties, peculiar properties of the laser beam, lasers have so many applications in different fields. Okay, so laser have so many applications in different fields. For example, it has application, different application in science, machining, communication, security and military, and medicine. Okay, so I will just give you the introduction to this list of these applications. Scientific applications. So there are so many scientific applications. So these lasers are used in many ways in scientific application. For example, it is widely used in interferometric techniques, in a Raman spectroscopy. In Raman spectroscopy, earlier we were using the ordinary radiations. Now this intense laser radiations are available, so we can use this laser in a Raman spectroscopy. Laser induced breakdown spectroscopy. In this one, firstly, this laser, yes, laser is very high. It has very high energy, so this energy can be used to break down the molecule to the different components, and then we can study the different fragments of the molecules. So it is laser induced breakdown spectroscopy. In atmospheric remote sensing, investigating nonlinear optical phenomena. So these lasers can be used to investigate nonlinear optical phenomena. So nonlinear optical means, in linear optics, we can say in optics, we study the reflection, refraction, transmission, how your radiations move, transmit from the different mediums. Okay, so in linear media, the frequency of the radiations are not changing. Frequency of the radiation, it is not changing. Only direction of the frequency it is changing. Okay, so we can see, we can have the reflection, refraction, and transmission. We can study this. Okay, so in linear media, in linear optics, as the intensity of the radiation is very less, so we can see only this, the linear optical phenomena. But as the intensity is very large, so this laser beam tries to modify the property of your medium, and it gives you non-linear optical effects. For example, just example. So in linear media, if you incident light of a frequency omega, so at the polar output you will get the frequency omega. Only there will be a reflection or refraction or transmission. Okay, but the frequency it will not change. It will remain same. It will be omega. It will only when it will change when it will absorb and re-emit the radiation. Unless and until absorption and re-emission, the frequency will not change. Okay, so your frequency it will remain unchanged in a linear optics. But in non-linear optics, the frequency may change. Means at the output you may have the frequency 2 omega, 3 omega, 4 omega, and so on. Okay, so there is a change in frequency. Means frequency is doubled. Means if you say the frequency at the output is 2 omega, means it is second harmonic generation. If you are getting the frequency at the output 3 omega, then we say the third harmonic generation. And it is only possible only when your radiations are very strong, the intensity is very large. So this can be, this non-optical phenomena can be observed only when if your laser is interacting your medium. Okay, so we say it is a nonlinear optical phenomenon. Optical Kerr effect, and these focal effect, these are the nonlinear optical effects. Lasers are also used in holographic technique. Employing lasers also contribute to the number of measurement techniques. Laser-based lidar, we use the laser in the lidar. We use these lasers, and it has so many applications in geology and seismology, remote sensing and atmospheric physics. Laser have been used aboard spacecraft such as in the Cassini-Huygens mission. In astronomy, lasers have been used to create artificial laser guide star, used as a reference object for adaptive optics telescopes. Laser may also be indirectly used in spectroscopy as microsampling system. The technique termed as laser ablation, which is typically applied to ICP-MS apparatus, resulting in powerful LA-ICP MS. ICP means it is inductively coupled plasma mass spectroscopy. So here laser is used to ablate or to remove the upper layer of your sample, or to make to remove the portion or parts of your surface of your sample, and then it is another is inductively coupled plasma mass spectroscopy. Okay, so in this laser is used for the ablation purpose. As well, since this laser is used in the spectroscopy, so laser is a monochromatic light and it is a very defined range of wavelengths. So these lasers can be used in so many spectroscopy. So it is used in Raman spectroscopy, in the laser induced breakdown spectroscopy. So we say it is LIBS. So lasers are used in spectroscopy. It is used in heat treatment. So in order to give the heat treatment to the surface of a certain material, so these lasers are used because lasers have very high intensity and it can hit the surface. Generally, carbon dioxide lasers are used to have the heat treatment of your different materials. In weather applications, the people are trying to use the lasers in weather application, but it is in an experimental level. It is not in an application. A lunar laser ranging. So when Apollo astronauts visited the moon and they planted the retroreflectors array on the surface of the moon, and if focus the laser beam from the Earth, so it will be reflected from these reflectors, and you can measure the distance between the Earth and Moon with the very high accuracy. In photochemistry, also we use the lasers. So you know this laser may be pulse laser or it is continuous wave laser. So if you consider the HEA laser, it is a continuous wave laser, means you will get the laser continuous laser at the output. But there are pulse laser also. So the pulse laser, for example, Indiac laser, nitrogen laser, these lasers are the pulse lasers, and they have the pulses of very short duration, and these pulses can also be reduced in this time scale, or you can make very small pulses, very big pulses of light for a very short time, that is picosecond or femtosecond. So if it is your pulse or width is of picosecond, then we say it is picosecond laser. If it is a femtosecond laser, femtosecond, then we say it is femtosecond laser. So this can be done by the mode locking process. And now you know in chemistry, if you say there are chemical reactions are going on, and during the we are getting so initially we are considering some chemicals, we are adding together, maintaining some environment, and we are getting final product. So during this process, these two initial chemicals are interacting with each other, they are reacting with each other and giving you final product. Okay, so certainly we are interested in the final product, but people are also interested in in what is going on during this reaction. Is there any short-lived molecule is present, or is there anything it is during this process of getting a final product? So in order to study that one, we require the very short laser pulses. So this, because this short-lived intermediate molecules, it may be lived for a very short duration, so that we shall require the laser light or light pulse of that much of duration or less than the lifetime of that short-living molecule. Okay, so this picosecond and femtosecond lasers are paving the way to study those short-living molecules during this total reaction. That is from initial chemicals to final product. So we can study the short-living molecules by using this picosecond and femtosecond lasers. In general application, you know, this laser barcode scanner is there, laser scanners are there, laser printers are there. So these instruments we are using every day. Microscopy. In microscopy again we use this laser in confocal laser scanning microscopy and 2-photon excitation microscopy. So this two microscopy, it makes use of laser to obtain blur film images of thick specimen at various depths. At various depths. Laser cooling, it is again a very important scientific application of the laser in a laser cooling. So in this technique, the laser is used. So you know, in this experiment or laser cooling experiments, the atom is trapped by the laser beams. It is incident laser beams, which is allowed to incident from the so many directions, and this the electric and magnetic field of this laser light, it is interacting with the your atom, and it is slowing down that atom and making that atoms cool, ions or atoms cool. So we say it is a laser cooling. So these lasers are cooling they are fixing their position of the atoms or ions, so that they are not moving from their position. Means we are making them cool. We are cooling that atoms or molecules, and this is said to be laser cooling. And we can, if we cool down the laser, you can say that your atoms are in the same energy level. So we can study here Bose-Einstein condensate. That is means all the atoms are in a only one energy state. Okay. Another interesting application of this radiation is the nuclear fusion reaction. So you know, the energy, the source of energy of every star is the nuclear fusion. So you know, there are two kinds of nuclear reactions: nuclear fission and nuclear fusion. So in nuclear fission reaction, heavier nuclei, they break down into a smaller or lighter nuclei, and it is emitting lot of energy. And we use that energy to heat the water, make it vaporize the water, and then run the turbine and get the electricity. Okay, so this nuclear fission energy we use, so in which the uranium, plutonium are generally used. These are the radioactive materials, and whatever the product we are getting, it is again radioactive material. It is a radioactive one. And then handling this radioactive waste, it is again very difficult. So we cannot just leave that waste anywhere. because it will emit the emit the hazardous radiation, and those hazardous radiations. So these are very fatal to the health. Or also it can do those radiations, that is gamma rays, alpha rays, especially gamma rays are able to make genetic changes. Okay, so that it is very whatever the waste we are getting from the nuclear fission reaction, it is a very dangerous one. Okay, but still, so in order to avoid this, the peoples they are packing that nuclear fission reaction waste into the lead boxes and dumping into the deep of the sea. But in future, after corroding that container, radioactive waste may come out of that one. Okay, so it will be again dangerous for all living beings. Now, another nuclear source of energy is the nuclear fusion reaction. So, nuclear fusion reaction is the source of every star, every star. So, energy source of every star, and it is confirmed that the 4 hydrogen nuclei fusing together to have the helium nucleus, and in this one, lot of energy is emitted. Okay, so that energy we can use to we can convert into the electric energy and we can use. Okay, so people are working on this nuclear fusion reaction. So this this nuclear fusion reaction, it is taking place at a very high temperature. It is around 6,000 Kelvin. Okay, so on Earth we can easily create that temperature, but confinement of that whatever the plasma it will develop at that temperature, it is very difficult. Okay, so people are working on that one. So in this case, the lasers are used. So these in this nuclear fusion reaction, the pellet of tritium and deuterium, that is isotope of hydrogen, tritium and deuterium, these are bombarded, or the lasers are inciding on this deuterium and tritium pellet from the 6 direction. It is the laser beams are inciding on this one from the 6 direction, and because of the high power laser, this deuterium and tritium are getting compressed. It is getting compressed, so that the there is a compression of the deuterium and tritium, and a lot of energy it is increasing, and there is a fusion of the deuterium and tritium to produce the helium nucleus, and a lot of energy is emitted. So this technique is said to be inertial confinement fusion. Inertial confinement fusion. So people are working on this nuclear fusion reaction by using these lasers. So we are getting this, we are achieving this nuclear fusion by using this laser, but whatever the energy we are getting from out of this reaction, it is very less as compared to the whatever the power we have used to develop the laser and other things. Okay, but in future we expect this nuclear fusion energy, or nuclear fusion reaction, it will be the source of energy for us. In military, there are so many applications. In a defensive countermeasure, lasers are used. So again, this laser are used for these defensive countermeasures, disorientation. Some weapons simply use a laser to disorient a person. One such weapon is the Hales green laser optical pumping. Lasers are used for the guidance. So laser guidance is a technique of guiding a missile or other projectile or a vehicle to a target by means of laser beam. Target, it is used for the target designator. This laser sight, it is used for the laser sight. It is used in eye-targeted laser, holographic weapon sight. Lasers are used in industrial and commercial application. So in the industrial and commercial application, we use this laser cutting. So This metal plate cutting, these lasers are used, laser welding, laser drilling, laser marking, laser cleaning, laser cladding. Again, harnessing, photolithography, optical communications. In optical fiber, these lasers are used. Laser pinning, guidance system, range, range finder, surveying, LIDAR, barcode readers, laser engraving, laser bonding, laser pointer, laser mice, laser accelerometers, OLED display. So in this case, so many this industrial and commercial applications lasers are being used. In entertainment, lasers are always used. So laser, laser lighting displays, the laser tag, laser harp. In surveying and ranging, laser rangefinder, laser level, laser altimetry, and satellite laser ranging techniques. These lasers are used. In medical applications are also the lasers are used. So in medical applications, lasers are generally used for the treatment and diagnostics. Treatment and diagnostics. So we can use for the treatment purpose and again for diagnostics purpose. So in treatment, it's covered everything from the ablation of tissues, that is removing bad tissues using high power lasers, to a photochemical reaction obtained with the weak lasers. So we can, this treatment, the use of laser in treatment, it is from the ablation of tissues, means burning the tissues and removing tissues, in which we require high power laser, and low power lasers, weak lasers are used for this photochemical reaction. Diagnostic, in a diagnostic, generally these lasers are irradiated, the particular portion is irradiated with the laser, and fluorescent signal it is received from that portion, and then the change in that, the fluorescent signal or the change in the optical parameters of that laser, it is being studied to diagnose the particular disease. In diagnostic laser system, we require these factors to consider this factor. A suitable excitation wavelength, we have to consider. Knowledge about the fluorescence properties of different chromosphere in tissues is we require. Origin of fluorescence spectra must be identified, and tumor seeking drugs. If you talk about in order to diagnose the cancerous tissue, this tumor seeking drugs, that is hematoporphyrin, is used to enhance the optical demarcation of malignant tumors. In surgical applications, these lasers are used for tissue heating, that is for the skin rejuvenation and tissue welding, coagulation, vaporization, fragmentation of tattoos, tattoo pigments, cold cutting, photoacoustic, that is basically it is lithotripsy, and photodissociation, that is non-thermal ablation of cornea in ophthalmology. Where lasers are used in retina treatment, in laser LASIK. So to correct the eyesight, we use this LASIK technique. We say laser assisted in situ keratomiliosis. So these lasers are used in this laser surgery. We use here also the laser. Eye surgery, we use this laser. In dermatology, that is for hair removal, we require lasers in the range 700 to 1000 nanometer. Skin resurfacing, 3 to 10 micrometer wavelength lasers. Vascular and pigment conditioning lasers, we require the lasers belonging to the wavelength region 532 to 600 nanometer. Ophthalmology, detached retina repair and retinal cancer treatment, we require. We use the laser. Stroke clot blasting via optical fiber, we use this laser. Laser are used to remove the red birthmarks This pulse laser can also remove the tissues. Generally, EAG laser, erbium, lithium, aluminum, garnet lasers are generally used. So lasers, there is laser angioplasty, and there are lasers are also used in dentistry for the faster healing, reduction, reduce risk of infection, decrease sensitivity, and less time in the dental glares, less bleeding, and less post-treatment discomfort. So there are so many applications of lasers we have. So I have just I have given just introduction to the what is the laser and its application. So if you have any question, then you can ask. Thank you. So if you have any query, then you can ask.
Hello. Very nice informative lecture.
So the restoring force will be very large. Okay. So as the restoring force is large, means the electric field force is electric field force because of the electromagnetic radiation is very large. So the restoring force it will be very large. So that's why this dipole it will start to oscillate with a very high frequency. It will be start to oscillate with very high frequency. It is greater than omega. So sometimes it may oscillate with the frequency 2 omega, 3 omega, 4 omega. Okay, so it will give if it is oscillating with frequency 2 omega, then it will emit radiations of a frequency 2 omega. It is 3 omega, then it will emit 3 omega. So there will be polarization. At a time, there will be polarization component of frequency 2 omega, 3 omega, 4 omega.
Any other questions?
Sir, for what purpose laser is used in light detection and ranging?
Ranging, was this ranging, you know, as if you, in order to measure the distance, measure the time between the sending, emitting pulse and receiving pulse, from that distance, from that separation between the time or the duration, we can find out the. So just as we use to measure the distance between the moon. So we send a laser pulse to the moon, and once it come a reflected pulse, we measure. So we can measure the time lag between these two pulses, and we can find out you know the speed of light. Just to travel that we can find out the distance from the speed of light and time required to travel that much of distance. Okay, from that we can find out the time. We can find out the distance.
Any questions again? Okay. If anybody?
Sir, how lasers are used for welding wires, sir?
Pardon?
Sir, how are lasers used in welding wires?
Welding wires. Laser it is used for the cutting, welding. It can melt. Means if you consider two wires are there, and if you irrigate that joint with this high power laser, so it will hit that and melt that portion, and it will melt. So very high power laser means Indian laser, copper vapor laser. Copper vapor, generally copper vapor lasers are used. Carbon dioxide laser and copper vapor. These are very high power energy, high power lasers. So they generate that much of temperature.
Thank you, sir.
Okay. Anyone? No questions. It is a very nice lecture delivered by the Dr. Muley sir, Professor in Hand, Department of Physics. So I would like to request Ms. Taili Daivadna to express the vote of thanks.
So thank you all students for hearing me, and I thank the organizing committee for giving me a chance to interact with you all. Thank you all. Have a good day.
Thank you.
Very good afternoon to on behalf of all students. It's my esteemed pleasure to express a word of thanks on the occasion of National Science. A great introduction is Dr. GGVS sir for accepting our invitation and for joining this program with us today. Thank you so much. Your motivation has truly inspired us. I thank our brilliant and the truly outstanding principal, Shri P, for always supporting and guiding us, as well as at time to Mr. Rahatgaonkar sir and Agrawal ma'am, and our all teacher staff who always puts a lots of efforts in making each one of us a good student. You have always been generous with your time and with your time with the students and need you. No matter what, thank you so much, dear teachers. And I'm also thankful to each and everyone for giving the auspicious time to us. Thank you so much.
Okay, with the permission of President, this program is over. Thank you very much, sir. Thank you, sir. Thank you,
Thank you, sir.
Muley, sir. Thank you very much.
Thank you so much, sir.
Okay. Hello.
Yes, sir.
Ah. Hello, sir.
हा हॅलो.
हा सर, आता लिहू शकता सर.
ठीक आहे. ओके.
खूप छान झालं सर लेक्चर. छान लेक्चर झालं. खूप छान. थँक्यू व्हेरी मच सर.
you